Hello, everyone. Welcome to Railway Engineering 101, a virtual course offered by the UC Berkeley American Railway Engineering and Maintenance of Way Association student chapter. This is the third lecture in a series of videos covering the basics of railway planning, engineering, and construction. Today, we will provide an overview of track components and turnouts, the backbone of our railway infrastructure. We will start our lecture by discussing the many different track components that are used in modern railway design. As a diagnostic, let's take a few seconds to identify everything we see in this photo. First, we have the rail. Note that there are two sides of the rail, the field side and the gauge side. Next, we have the tie, ballast, spike, tie plate, and rail anchors. We'll talk more about each of these components in detail. First, we have the rail itself. The rail serves to transfer the train's weight to the cross ties, provide a smooth running surface, and guide the train wheels. While early rails were wooden and cast iron, modern rail is made of continuously cast steel and can be sold and shipped in up to 1,500-foot pieces. Over the years, the shape of the rail cross-section has changed. The current shape is the inverted T cross-section, which was first produced in 1831 and has been the North American standard ever since. However, the exact shape of the rail cross-section can still vary and is known as the rail section. The key components of the rail section are the foot, web, and head. The foot of the rail is what distributes the weight of the train to the ties below. The web elevates the train above the ties, giving clearance for the wheel flanges and keeping the train clear of debris between the rail. The rail head is what actually supports the train's wheels and is therefore the part of the rail section that experiences the most wear. Rail can be identified in the field based on branding and stamping. Branding is the raised characters on the web of the rail that identify the weight, section, manufacturer, year, and month rolled. Stamping is the hot stamped characters on the opposite side of the web that identify the heat number, individual rail letter, strand number, and method of hydrocarbon elimination. The weight of a section of rail is measured in pounds per yard. Over the last several decades, the rail weight used for mainline tracks has steadily increased to accommodate heavier locomotives and rolling stock. The most commonly used rail weight today is 136-pound rail. The 115-pound rail is still in service in many places, and 141-pound rail may be used in turnouts in particularly high traffic areas. In this photo, we read that the rail is 132-pound rail. Next, we can read the section code, which signifies which engineering group created the design standard for the rail section. In this photo, we read RE, which indicates that the rail section is manufactured to an ARIMA standard. Next, we may be able to read a code that signifies if the rail is specially treated. VT stands for vacuum treated, which is a process used to remove excess hydrogen from the rail during cooling. CC, on the other hand, stands for controlled cooling, which is another method for hydrogen removal. Removing hydrogen from the steel improves the durability of the rail, resulting in a longer service life and higher safety. Next, we can read the rail manufacturer. In this case, PST stands for Pennsylvania Steel Technologies. Finally, the year and month of production are indicated. The year is indicated directly, while the month is indicated in hash marks. For example, for this rail brand, we can determine that we have 115-pound rail, an ARIMA section, controlled cooled, Workington, Tennessee mill, and produced in July 1974. In continuously welded rail, welds are used instead of joint bars to connect pieces of rail. New rail is rolled in 39 or 80-foot lengths, after which it is welded at the factory into sections up to 1,600 feet in length. These sections can be transported by rail to the project site, where they are themselves welded together to form a single continuous piece of rail. The elimination of joints both improves the ride quality, which is particularly important in passenger operations, and it also significantly reduces long-term maintenance requirements. As a result, you should specify the use of a continuously welded rail whenever possible in track design. Next, we have the tie. The purpose of the tie is to transfer the load of the train from the rail above to the ballast below and to maintain proper gauge, which is the spacing between rails. Ties are typically made of timber or concrete, though steel and composite ties may also be used in special cases. The selection of tie material is dependent on track usage, traffic volumes, climate, and economic considerations. Because of differing structural properties and maintenance requirements, it is not recommended to intermix ties made of different materials. We will start with timber ties. Timber ties include both hardwood and softwood ties. Hardwood ties are denser and more rigid, offering greater mechanical resistance against plate cutting, gauge spreading, and spike hole enlargement, which are all various forms of tie defects. As a result, they are the preferred choice for switch and track ties. In contrast, while softwood ties are more rot resistant, they are less rigid and are thus not as effective in transmitting loads to the ballast section, experiencing a shorter service life as a result. However, softwood ties are used frequently as bridge ties as they absorb some of the dynamic load that would otherwise pass directly to the bridge superstructure. Regardless of the wood type, all timber ties must be pressure treated with preservatives such as creosote to protect them from insect and fungal attack. Timber track ties, also known as cross ties, are graded with nominal dimensions of 7 inches by 9 inches by 8.5 feet for mainline use, with siding and industry tracks typically receiving lighter 6-inch by 8-inch ties and grade crossings receiving longer 10-foot ties. Mainline timber track ties are usually spaced with 19.5 inches between tie centers. Gang plates may be used to extend the tie service life by preventing end splitting failures. There is much debate surrounding the suitability and cost effectiveness of using secondhand ties. If secondhand ties are used, do not turn the tie over, as the previously buried surface will deteriorate rapidly once exposed to air. Instead, make sure to insert the tie as it was originally oriented. Timber switch ties are always produced with a nominal cross section of 7 inches by 9 inches, but range in length from 9 feet to 24 feet and are produced in 6 or 12-inch increments. While the primary use for these ties is in turnouts, these longer ties are also used in bridge approaches, crossovers, hotbox detectors, grade crossings, and at insulated rail joints where more support is required. Concrete ties are made out of pre-stressed concrete containing reinforcing steel rebar. These ties weigh about 800 pounds each, which is significantly heavier than the 250-pound timber ties. This makes them harder to install, though they typically have longer service lives. Concrete ties are typically used on mainlines with heavy tonnage and in areas with sharp curvature, as they offer greater stability for track geometry. Concrete ties are typically installed with 24-inch centers, but can be specified with tighter spacing on sharp curves. A specialized pad is inserted between the base of rail and the plate to cushion and absorb the load and to prevent abrasion of the rail seat. This pad will wear over time if not replaced and can lead to the failure of the tie if it does so. So, let's take a step back and ask ourselves, what are some potential advantages and disadvantages of using concrete ties instead of timber ties? The advantages of concrete ties include that first, unlike timber ties, concrete ties do not rot. Second, concrete ties are more fire resistant than timber ties. Since concrete ties are heavier than timber ties, they also resist lateral movement and tend to maintain track geometry more effectively. Finally, in general, concrete ties are more durable than timber ties, providing for a longer service life and requiring less ongoing maintenance. However, concrete ties also carry a number of disadvantages. First, they have a higher installation cost, with an average cost of $200 per concrete tie as compared to only $95 per timber tie. Second, concrete ties are far more susceptible to damage from derailed rolling stock. While timber ties may be simply gouged by a derailing wheel, concrete ties tend to shatter upon impact, and they can often do so internally. As a result, it is common practice to replace all concrete ties that dragging equipment or derailed cars have traveled over due to the risk of internal fractures, whereas timber ties may be replaced based on visual inspection. To help mitigate this risk, railroads will often install dragging equipment detectors with a closer spacing in concrete tie territory as opposed to timber tie territory. Finally, concrete ties are far more rigid than timber ties, so they do not absorb as much vibration from passing trains. As a result, the underlying ballast will tend to degrade more rapidly. Second, why do many railroads use timber ties in concrete tie territory? Here we see BART using timber ties for their turnouts, and many freight railroads do the same thing. Timber ties are often preferred for use in turnouts and other special track work for the following reasons. First, concrete ties must be designed for a specific turnout geometry such that the rail seats align, while the flat, uniform surface of wood ties makes them far more flexible, and they can be used in any turnout geometry. Second, as mentioned previously, concrete ties are far more susceptible to damage from derailed rolling stock. Finally, if the switch ties are damaged, it is much easier to maintain a reserve supply of standardized timber switch ties than it is to stock many sets of customized concrete switch ties, simplifying and expediting emergency repair efforts. Finally, we will briefly discuss steel and composite ties, which are not very common in the US. Steel ties can be used with a thinner ballast section, so they are occasionally used in tunnels and in areas with limited vertical clearance, or in yards for both switch and track applications. However, Steel ties are not widely used in mainline applications due to the problems associated with the shunting of signal systems. Composite ties can be produced from recycled plastics, with additional polymers added to ensure the tie meets strict performance requirements. Significant research continues to be performed on the viability of composite ties. For now, composite ties have been installed in a few locations on both transit and freight properties. Next, we have the ballast section. The principal purpose of the ballast section is to transfer and distribute the applied load with diminished unit pressure to the subgrade beneath. The ballast section also serves to provide drainage and resist lateral, longitudinal, and vertical movement of the ties and rail, ensuring stable track geometry. Key considerations when choosing ballast are hardness and toughness, durability and resistance to weathering, freedom from deleterious particles, workability, compactability, cleanability, availability, and low initial cost. The three ballast types that most nearly meet these ideal requirements in order of preference are granite tarp rock, hard limestone, and blast furnace slag. Other materials such as weaker limestone, prepared gravels, decomposed granite, volcanic ash, pit run gravel, and coarse sand may also be used as a last resort. The depth of ballast required is a function of the supporting capacity of the subgrade, where the depth of ballast beneath the tie must be sufficient to distribute the pressure to within the bearing capacity of the subgrade. Usually, a minimum depth of 18 to 24 inches split between the ballast and subballast is required to achieve uniform distribution. In general, ballast should be dumped such that it is level to the top of ties for maximum track stability, as track stability derives from the frictional interface between the bottom and sides of the tie with the ballast. A ballast shoulder width of 12 inches beyond tie ends is considered ideal in both tangent and curved track, and side slopes are typically 2 to 1 or 3 to 1. Next, we have rail joints. The purpose of the rail joint is to keep the two ends of the rail aligned laterally, longitudinally, and vertically. Each rail joint is made up of two joint bars, seen in the photo above. These joint bars are mounted between the head and base of the rail to keep the ends aligned and are tightened together by the appropriate track bolts, reducing movement while permitting some longitudinal movement for thermal expansion. The joint is considered the weakest part of the track structure and should be eliminated whenever possible. Joint bars must be matched to the appropriate rail section. Failure to do so will result in an inadequately supported joint and will promote rail defects such as head and web separations and bolt hole breaks, as well as bar failure. As a result, the use of incorrect joint bars is considered an FRA defect. There are three basic types of rail joint: the standard joint, compromise joint, and insulated joint. Standard joint bars connect two rails of the same weight and section. Joint bars are typically 36 inches in length with 6 bolt holes. Joint bars used to be installed every 39 feet in traditional jointed rail, but they are still used for temporary joints in continuously welded rail when the rail is cut for maintenance activities such as de-stressing. A minimum of 2 bolts must secure each end of any joint in continuously welded rail. To preserve a good rail end condition for welding, only drill the 2 outer holes in each rail end and eliminate temporary joints as soon as possible to minimize rail end wear. Compromise joint bars connect 2 rails of different weights or sections. They are constructed such that the bars align the running surface and gauge sides of the different rail sections. The use of transition rails, which are specially manufactured rails that transition slowly between 2 rail sections, has reduced the use of compromise joints in mainline track. Transition rails are also used to connect existing and new track work, as worn rail will have a slightly different section than new rail. Insulated joints, or IJs for short, are used in tracks with signal track circuits. They isolate different track circuit sections by preventing current from flowing between the ends of 2 adjoining rails. Insulated joints also use an insulated end post between 2 rail ends to prevent them from shorting out. The most common type of insulated joint is the bonded insulated joint. Steel joint bars are encapsulated in insulating polyurethane, and an epoxy resin is used to glue the insulated joint bars to the rails. Bonded IJs are typically sold pre-assembled in various lengths, and the completed assembly can be welded directly into the track structure. The purpose of the track bolt is to secure rail ends together at a rail joint by tightening the joint bar to the rail section. Track bolt sizes vary by rail section, and it is up to the railroad to specify the proper bolt diameter and length. Track bolts are normally supplied with an oval neck to prevent the bolt from turning when torqued, allowing for easier fastening, and are used with square nuts or with or without spring washers. Bolt heads and nuts alternate sides of rail in a typical joint to limit damage to the exposed end of the bolt in a derailment. Next, we have the tie plate. The purpose of the tie plate is to provide a smooth and uniform bearing surface between the rail and tie, distribute the load from the rail to the tie, and provide a solid foundation for the rail to help maintain gauge. Tie plates are not reversible, as they are typically canted at a 1 to 40 slope to raise the field side of the rail, helping to distribute the wheel load to the ties and assisting the wheels track around curves. Tie plates are produced as single shoulder or double shoulder plates. Single shoulder plates are used with lighter rail sections, while double shoulder plates are typically used with heavier rail sections of greater than 100 pounds. There are different tie plates for different tie fasteners, such as traditional track spikes or pandrel clips. Speaking of fasteners, the purpose of rail fasteners is to secure the rail to the tie plate and tie both vertically and laterally. This helps to maintain track gauge between the running rails and prevent plate cutting of the ties, where the tie plate begins to cut down into the surface of the tie. The most common rail fastener is the track spike, which is driven through holes in the tie plate to secure the rail to the tie. Line spikes secure the rail to the tie plate and simultaneously secure the tie plate to the tie. In contrast, anchor spikes only secure the tie plate to the tie and can serve as additional support and curves to help maintain gauge. Anchor spikes are not always used. Spikes come in different lengths to ensure an adequate length of spike penetrates into the tie. 6-inch spikes are typically used for larger rail sections. Pandrel clips use special tie plates and a wraparound clip to hold the rail more securely than track spikes, and each clip can hold around 2,500 pounds of force. As a result, railroads often use pandrel clips through and around fixed points where the rail cannot be allowed to move vertically or longitudinally. These include turnouts and special track work like diamonds, as well as grade crossings and bridges. Pandrel clips are also used in concrete tie territory, as traditional track spikes cannot be driven into a concrete tie. Curve blocks are another type of specialty rail fastener that help maintain gauge in curves by forcing an inwards rail cant and preventing the outer rail from rolling over. Curve blocks are typically spaced on every third tie. Finally, we have rail anchors. The purpose of rail anchors is to control the longitudinal movement of the rail, which may be caused by changing temperatures, grades, traffic patterns, and the braking action of trains. Anchors are applied at the base of rail directly adjacent to the tie, as the tie is embedded in the ballast and resists longitudinal movement. However, anchors must be fully applied and tight against the ties to be effective. Continuously welded rail typically requires a 50% box anchor pattern, where anchors are applied on either side of every other tie. The 100% box anchor pattern is required for 200 feet on either side of fixed points like grade crossings, turnouts, and bridges. Rail anchors are not used alongside pandrel clips or on concrete ties, as the pandrel rail fastener system serves the same purpose. Next, we will discuss a number of specialty track components with which the engineer must be familiar. To start, why would a railroad ever want to intentionally derail a train? The purpose of a derail is to secure unsecured rail cars, preventing the unintentional movement of unsecured rolling stock from following a specific track, commonly the main line. As a safety measure, many railroads require the derail to be left in the derailing position, regardless of whether there are cars occupying the track. The engineer must select an appropriate model of derail for the given rail section. An undersized derail will not properly cover the railhead and may not derail a car as intended, while an oversized derail may be damaged from improper support from the railhead. There are multiple different types of derails. Hinged derails are manually applied to the track and rotate in a vertical semicircle to move the derail on or off the trail. Sliding derails are mounted on two switch ties and are operated by a switch stand. Switch point derails resemble a normal turnout that essentially leads to nowhere. These derails are used in special locations, such as at the bottom of steep grades or where high-speed movement could knock a hinged or sliding derail off the track instead of derailing the movement. Finally, portable derails can be temporarily mounted to the rail to protect workers and equipment in mainline or shop locations. The purpose of wheel stops and bumping posts is to prevent rail cars from rolling off the ends of subtracks and to protect structures from damage. Wheel stops can be classified as rigid, which bind securely to the rail, or cast, which are easier to install and move. Bumping posts are braced blocks at coupler height and are used for heavier service, such as in passenger stations. The purpose of gauge rods is to maintain track gauge, supplementing ties and preventing lateral movement of rails. Gauge rods may be installed permanently in sharp curvature locations or temporarily in defective tie condition areas, though they should not be considered a permanent fix. Expansion joints are designed to accommodate the longitudinal expansion and contraction of rail, maintaining the continuity of the running rail. Expansion joints are common around fixed points such as bridge abutments and near special track work such as diamond crossings. Expansion joints are also common on open deck bridges because rail anchors are not used with softwood bridge ties, so the expansion of the rail must be accommodated through other means. Miter rails are used whenever track is to be opened and closed at frequent intervals, such as at drawbridges and swing spans. The two rails are either cut at a long angle or paired with a third outer transition rail to maintain a continuous running surface. In this photo, the outer rail is raised slightly to lift railcar wheels as they transition between the two stock rails, which can be clearly seen from the wear pattern on the rails. Finally, guardrails are used on bridges or tunnels to prevent derailed equipment from falling off an overpass or the deck of a bridge, striking the sides of a structure, or piling up in a tunnel. Inner guardrails are typically made of a standard T-rail section, though they are typically shorter than the running rail section. Outer guardrails, on the other hand, are typically standard timber members. Once again, these may be implemented on bridges, tunnels, and highway overpasses, though their use is discretionary to the railroad. Next, we'll talk about turnouts. We will start with basic turnout concepts. Turnouts are also commonly referred to as switches, though the switch technically only refers to the movable section of the turnout, which consists of two switch point rails operated by a switch mechanism. The stock rails are the outer rails that the switch points bear against, and the closure rails connect the switch points to the frog. The frog is the device at the intersection of the two running rails that allows the flange of a wheel moving along one rail to cross the other. Next, we will cover basic turnout terminology. The straight side of a turnout is called the main track, or straight movement, while the curved side of the turnout is called the diverging route, or movement. A facing point move is conducted from the switch points toward the switch frog for either route, while the trailing point move is conducted from the switch frog towards the switch points for either route. The point of switch, or PS, is the location where the straight or diverging route is selected. The heel of switch, or HS, is the location at which the switch points pivot about. The switch itself is defined as the area between the point of switch and heel of switch. The toe of frog, or TF, is defined as the point where the frog connects to the closure rails. The point of frog, or PF, is the point at which the train wheels cross over the other rail. The heel of frog, or HF, is the joint location behind the frog. Finally, the last long tie, or LLT, is the location of the last single tie that supports both straight and diverging movements. Technically, the turnout is defined from point of switch to heel of frog, but we often include all track work up to the last long tie as part of the turnout. A quick note about the point of frog. The point of frog is blunted so that it does not break off under traffic. Thus, the actual point of frog is usually some distance behind the theoretical point of frog, which is where the two gauge lines meet. As a result, we usually take the half-inch point of frog as our point of frog, and it is located where the gauge lines on either side of the frog are a half-inch apart. There are three main kinds of turnouts. Lateral turnouts are the most common, in which the main track is straight and the diverging movement must run to the right or left. Lateral turnouts are defined as right-handed or left-handed based on whether the diverging track runs to the right or left when facing the turnout points. Since the main track runs straight through the turnout, a reduction in speed is only required for the diverging route. Equilateral turnouts are common at the ends of double track territory, where both tracks are considered main tracks. Both routes diverge, but both require a smaller reduction in speed for both routes. However, the benefit of an increased speed may be negated by the fact that a train waiting at the end of the two tracks may not reach the maximum speed until far past the turnout, so care must be taken when deciding to use an equilateral turnout. Finally, lap turnouts are used in areas with limited space, such as hump yards, and contain two sets of switch points and three different frogs. As mentioned previously, the purpose of a switch is to direct at will the wheels of a train from the track upon which they are running. The switch itself consists of two switch point rails connected by switch rods, which are operated as a unit. The switch point rails are of a full section on the heel end and are tapered to a quarter-inch or half-inch point at the other end. Samson switch points mate to beveled Samson stock rails, allowing the point to tuck under the stock rail, protecting the switch point from impact. Standard switch points are typically used for lighter rail sections of 100 pounds or less, while larger rail sections on mainline tracks typically use Samson stock rails. Samson switch points must be used with Samson stock rails, as incompatible points may lead to point failure or derailment. Switch rails vary in length from 11 feet to 39 feet, and even longer for high turnout numbers, depending on the weight of the rail and curvature of the turnout. During the switch operation, the point of switch moves a distance of around 5 inches, which is called the throw. Switch mechanisms can be either hand-operated or powered. Hand-operated switches can either be rigid or swing switch type. Spring switches allow the points to close automatically after being trailed through from the diverging side. Powered switches are operated by an electric switch machine. Dual control power switches can be operated manually or thrown remotely by a dispatcher. The frog is the device at the intersection of the two running rails that permits the flange of a wheel moving along one rail to cross the other rail. The frog includes the frog nose, frog wings, and guardrails. Guardrails typically accompany frogs to prevent misrouting and derailments and to protect the frog point from impact. The guardrail captures the back of the flange of the wheel opposite the frog and guides the other wheel through the throat opening of the frog. The frog number is defined as the ratio of run to spread and determines the turnout number and length. There are many different types of frogs, including RBM frogs, spring frogs, OWLS frogs, bolted rigid frogs, and movable point frogs, and we will review them briefly. Rail-bound manganese frogs consist of a one-piece manganese casting surrounded by binder rails. This is a heavy-duty frog used on mainlines due to its durability. The spring frog provides continuous support for the wheel as it moves through the flangeway. The frog has a movable wing rail that is held closely by a spring assembly and can automatically open and close for diverging movements. The spring frog is used for trackage with predominantly mainline traffic, especially in higher speed applications, as there is less pounding on the frog and it provides a smoother ride. The disadvantage is that this frog requires more maintenance than a traditional RBM frog. Movable point frogs are equipped with a movable frog nose, allowing the frog to provide a continuous running service to both normal and diverging routes. As a result, these frogs are more common in high-speed, high-number turnouts where both normal and diverging routes must operate at maximum speed. These turnouts must be equipped with a separate motor to align the frog nose and are more maintenance-intensive than traditional frogs. One-way low-speed frogs, or OWLS frogs, provide a continuous running service to mainline movements by requiring the diverging movement to lift over the main rail, ramping up and down and tracking over the main rail in flange-bearing mode. These frogs are commonly found on main lines leading into spur tracks with little use, as there is a 10-mile-per-hour speed limit for diverging traffic. Bolted rigid frogs are made out of standard machined rails bolted together. The straight route of the side of the frog is continuous, whereas the diverging side of the frog route is milled to intersect the straight side frog point rail. These frogs are inexpensive to fabricate and are used frequently in yards and secondary lines. As a quick exercise, let's find out the type and number of this frog. First, we can identify this frog as an RBM frog. Second, by measuring the ratio at which the spread and length of the frog, we can determine this is a number 10 turnout. To give some intuition for how the frog number impacts the length of the turnout, here is a comparison of various turnout numbers. For reference, many new turnouts in mainline trackage are number 24 turnouts, which are over 200 feet long. Finally, we will briefly discuss railway crossovers and crossings. Crossovers are implemented to allow trains to cross between parallel tracks and are especially common in double main territories. Single crossovers can be considered as two turnouts, with the track between following the frog angle of the turnouts. Double crossovers are essentially two single crossovers overlaid on top of each other, and thus consist of four turnouts with a diamond crossing in the center. While double crossovers are more expensive to install and maintain, they have a significantly smaller footprint, so they are commonly used in yards, stations, or transit applications where space is limited. A crossing, also known as a diamond, is a device used at the intersection of two tracks, allowing them to cross at grade. A crossing consists of four frogs and the necessary connecting rails. The crossing angle is defined as the angle between the track center lines at their intersection. For locations where a heavy tonnage route crosses a light tonnage route, one-way low-speed frogs can be used to allow for higher speeds and reduce maintenance for the heavy tonnage route. Finally, slip switches are used to allow intersecting tracks to cross at grade and allow trains to transfer between intersecting tracks. They consist of a small angle crossing and a pair of connecting tracks placed entirely within the limits of the crossing. Both single and double slip switches exist, where double slip switches allow for full freedom of movement between any pair of tracks. Since slip switches are by far more compact than combinations of diamonds and crossovers, they are commonly implemented in dense yards, passenger stations, and transit applications. That's all I have for today. Thank you for watching, and make sure to watch the other videos we have to offer.